Hello and welcome to this video on circular motion. Specifically, we're going to start talking about changes in velocity and how circular motion works. So here we have two velocity vectors. We can give them labels. This is 3 meters per second north and 3 meters per second east, for instance. And in both cases, you have the same speed, the same number. If you're in your car driving these, your speed would be the same. It would be 3 meters per second or 10 miles per hour, whatever. But the difference between these is the change in direction. They're not pointing in the same direction. And because velocity is a vector and thus is direction dependent, these are different velocities. What we have here is a change in velocity. If we want to talk about or measure this change in velocity, what we can do is we can line the vectors up tail to tail and draw a new vector from where they were to where they are now.
This will be your change in velocity, which, if you put it over your change in time, becomes your acceleration.
My acceleration is in this direction. Now, this is a average acceleration. It is how this changes over time. And it is representative of what the overall acceleration will be over time. Now, this scenario here seems a little far-fetched, a little out there, but imagine you're going down the street and you make a right turn. And suddenly this acceleration, this change here occurs. Now, changing velocities happens whenever you change the numerical value or the direction. So for instance, in these cases, we have 3 meters per second and 5 meters per second. Make sure you always label. And if you compare the 3 to the 5, it's fairly easy to see that your acceleration is the difference between the two, or the 2 meters per second squared. Your delta V is 2 meters per second, and if it happens in 1 second, which may or may not, will be meters per second or meters per second squared. We're going to assume that all changes occur in 1 second. For sake of example, here I'm slowing down. My delta V over delta T, to be specific, is -1 meter per second squared. Because in this case, I'm going from 3 to 2. I'm reducing. Notice how my acceleration is to the left, but my velocity is still to the right. I'm slowing down, but I'm still moving forward. The last one's the most tricky because you're going from 4 to -4. And while you can think about it a couple different ways, the easiest way I find is just line them up and what's the total difference here? What's the change here? Well, we've gone from +4 to -4, or a total of 8. In this case, my velocity change is 8 meters per second squared.
This is a typo. This should be -8 meters per second squared because it's final minus initial for any delta calculation. So -4 minus 4 would give you -8. In this case, meters per second squared.
Now, in each of these cases, all we did was just measure the difference between the arrows. And if we line them up, we can see how it just makes that difference there for us. Some of them are better drawn than others, but there we go. What happens, however, when we start moving in a circle? So the world is not made of perfect circles. There are very few of them out there, but there are some places where they do exist, roundabouts, for instance, or in most cases, you can model going around a corner or a curve as a circle, and it's close enough to work. Now, to start, let's talk about how fast we're going at each of these points. Here, here, and here. Because the car has a velocity. It's traveling forward. The velocity at the instant we look at it is this direction. This is what we refer to as an instantaneous velocity. Now, an instantaneous velocity, again, is just what it sounds like. It's the velocity at a moment in time. It's what we've been using for all of our calculations and examples. At this specific instant, how fast are you going? What direction are you going? And we can do the same, talk about it here. Now, we can also talk about this in terms of a circle, because in circular motion terms, these velocities are instantaneous velocities, but they're also called your tangential velocity, or your v sub t. These are the velocities that if you stopped going in a circle, you'd continue on at this velocity. It's called such because the line is tangent to the circle, or it would, if you continued it on in both directions, would only touch the circle at a single point. Now, in this example here, my exponential speed is the same. Say it's 3 meters per second all the way around. And what I want to start looking at is, what is my acceleration? Well, I can start right here and looking at the two of these, and I've done this one already. I did it here. My acceleration will be down and in. But what if I want to start looking at smaller and smaller values? What if I want to start looking at a less amount of time? Because the average acceleration, or the average velocity, is over a larger period of time. But if you take that period of time and shrink it down, more accurately, for those of you who understand calculus, as delta t goes to 0, as it gets smaller and smaller and smaller, your average velocity will slowly change into your instantaneous velocity. So to get from here to here, my acceleration looks like so. So that way I kind of go like that to get from this car to this car. But what if I wanted to talk about from this car to, say, what if I choose this point, let's say here. I'll draw my line in like so. Now, when I move this over, line like so, if I take this line and move it in, notice it starts doing this. Now, this is an imperfect representation. I am not the greatest at drawing, but notice how as we keep getting closer and closer together, the line keeps straightening out more and more and more. If we did this perfectly, if we did this with perfect drawing, perfect calculations, it ended up getting an acceleration pointing towards the center of the circle. This acceleration here is called a centripetal acceleration. Let's go ahead and spell that out. Now, this acceleration exists because of a force. More accurately, because there's an acceleration, there has to be a force. Newton's first law. And this center-seeking or centripetal acceleration has to come from some kind of force. If you take something and swing it around in a circle, your finger is providing that center-seeking force. Or the rope, if you do it the other way. In the case of a car, your tires
are providing that centripetal force via the friction between the tires and the pavement. Whenever we talk about a centripetal force or centripetal motion or circular motion, the force that provides the center-seeking acceleration becomes from a known force but is pointing in towards the center of the circle.
To recap, in order for there to be circular motion, there needs to be a centripetal acceleration and a centripetal force. Or in other words, there needs to be a force pulling towards the center of the circle, and there needs to be a force pulling, and that force will provide an acceleration on the object, whatever force that is. So in this case, the frictional force from this car would be your centripetal force. So let's talk about free body diagrams for what this looks like. Let's take a look at, say, this car here. Now, we can look at it from the side, like we kind of are. We'd have normal and such, but it's kind of we need to end up drawing in 3 dimensions. So instead of drawing from the side, let's draw it from the back. Okay, now we can all see why I didn't go to art school and such, but I'm drawing a car for this sake of argument. Let's talk about the forces acting on this car. You have the gravitational force pulling it down, its weight. You have the normal force pushing up, which stops it from falling into the earth. But you also need to have a force that keeps it moving in the circle. In this case, your friction, which is acting as a centripetal force here, pulls it in a circle. And this allows this car to corner, to turn. If everyone talks about high quality tires, they're talking about good rubber and good grip on the pavement. So the free body diagram for this here looks like this. And notice how we have an unbalanced force in the form of friction, which is providing the ability to corner, to circle here. Let's take a look at an example. So here we have a pendulum. The path of a pendulum is circular or close enough for most approximations. It's just this part of the arc here. What I want you to be able to do is draw a free body diagram for each point on the circle, A, B, and C. I'll do A, and then you'll do B and C on your own. So at A, what are the forces acting on the pendulum? Well, start by drawing your box. You have gravity pulling it down. And you've got tension pulling it up and to the right. You'll notice that my tension force is slightly larger than my force of gravity, and this is because I need to have a net force towards the inside of the circle, up and to the right, in order an acceleration. Go ahead, do the other ones on your own. Give it a try. Okay, so in this diagram, I've done B and C. B at the bottom is the lowest point, and it's fairly easy. It's only got the tension pulling up and the force gravity pulling down. But you'll notice that the tension is notably larger than the force gravity. That's because I'm moving in a circle. There's circular motion going on. There has to be a net force towards the inside of the circle in order for there to be an acceleration. If this wasn't true, if the pendulum was just standing still, these two forces would be equal. But because the pendulum is swinging, because it's moving back and forth, there has to be a net force towards the center of the circle to provide that centripetal acceleration. C is just the mirror image of A, pointing towards the inside of the circle with the net force up in it. And there you have it. That's how we draw these free body diagrams and the such. Thanks for watching. Have a good day.